Okay, hello everyone. Good to see you all. So let us go back to the course. What have we done last time? We have seen a problem called the halting problem, which was a decision problem. We had to say if yes or no, the encoding of ij correspond to ti of j, which halts, a halting computation. And via a diagonal argument, we showed that the halting set is an uncomputable set, so there's no decider for the task that I mentioned, a decider being a computable decider, obviously. And we showed that by contradiction. Now, the second hour, we saw that, well, it also means, since, axiomatic systems in mathematics entail that we can recursively enumerate all theorems, it also means that we cannot hope to find a proof in general of looping computations. Otherwise, we could decide the halting problem. Now, technically, I'm done for computability theory. We have all that we need to move into algorithmic information from now. However, there might be a general feeling of unsatisfaction when we could say, oh, well, the halting problem is a very sketchy one. It will not really occur often. So what we'll do today, we'll see that no, it arises in many, many, many other problems. It contaminates many other problems. Before I go there, I also want to say that what we've done last time in terms of a result of incompleteness, I think I called it incompleteness a la Turing, is not going to be our final one. We're going to have yet one more view of incompleteness that is enabled by algorithmic information theory. It's Chaitin incompleteness, and it's even more quantitative than Turing's. So yeah, it will not be the final take on incompleteness. So what I was about to say, maybe today's section is called Rice's theorem. And as a motivation, I said that the halting problem contaminates many other problems. In a nutshell, Rice's theorem states that any non-trivial property concerning the behavior of Turing machines is uncomputable. So not just does this machine halt on that input, but any non-trivial question that you might ask for a Turing machine or a piece of code, if we put it into modern terms, is also going to be undecidable. In a nutshell, Rice's theorem states that any non-trivial property concerning the behavior of Turing machines let me put it, or of computer programs in modern terms, is undecidable. All right, we'll see what we mean by non-trivial and by properties concerning the behavior of Turing machines. I was debating how I should teach this, and I could do the abstract proof in the most general case, but I feel like we miss the gist of the idea if it's too remote from a concrete example. So in fact, I'm going to do one example, a very, very narrow case of trying to decide the behavior of a Turing machine. And we're going to see how, what I mean here by the halting problem contaminates that problem. And I'm going to finish by stating Rice's theorem, and you're going to basically understand how to prove it by the example that we would have done. So yeah, I think it's more enlightening to just do an example, which also permits me to write in blue. Example. Consider the successor function. Okay, I was trying to find like an easy function, a function that we're all familiar with. Could have chosen the square function or any function. I took the successor function. So what is the successor function? I'll denote it S. It's a function from the natural to the natural, and it maps n to n plus 1. It's obviously a computable function. In fact, it's a total computable function because it's always defined for all input. And so in the enumeration phi 1, phi 2, phi 3 of all partial computable functions, the function S occurs many times. Right? It's a computable function. This enumeration here, phi 1, phi 2, phi 3. In fact, we started by enumerating all Turing machines, and each Turing machine computes a partial computable function. And so Turing machine number 1 computes partial computable function number 1, and so on, 2, 3. And S is just a function, but in this list of Turing machines, or in this list of partial computable functions, the function S occurs many times. How many times, in fact? Infinitely many. Right? I left space, infinitely many. Why? Because write down one Turing machine which does compute the successor function. And then from that Turing machine, you can, generate an infinite family of dummy modifications of that Turing machines by, for example, adding more states which will never be visited and that will have like rules that you choose. And you can, so from one Turing machine, you can modify it in infinitely many ways to generate a family of Turing machines. In modern term, it would mean that once you have one computer program, you have infinitely many computer programs that does the successor function. Cool. So this just justifies that it occurs infinitely many times. We've seen it for the universal Turing machine. Now we also see it for any function, basically. Now what we want to consider is a set IS equal to the set of all indices that correspond to a function that is actually computing the successor function. Okay, so it's the set of i's. Usually my eyes don't look like that. Set of i's such that phi I is equal to s as a function. And our problem is IS decidable? Okay, this is, and this is I sub s. Just to remind you those notions, a set is decidable or computable if its characteristic function is computable, or another way to say it, if there exists a decider for that set. A decider for that set is it's a Turing machine which will always halt and will say yes or no, I is in the set. So I'm expanding on what that means, i.e., does there exist a Turing machine that compute the decider DIS, the decider of the set IS, which on input I is going to say yes or no, namely 1 or 0. It's going to say 1 if I is in the set. I'm going to be a bit more explicit. If I is in the set, it means that I is an index of a function phi I, which does compute s. So if phi I is equal to s, it's the same as saying that I is in the set. And 0 if not. Question mark. Does there exist a Turing machine that computes this? Do you understand the question? Yep. So the decider has to look at I. Obviously, I is like a bit of it's a cryptic way of like encoding the rules of the Turing machine. But you remember that from I we can compute E of Ti, which was the encoding of the table of rules of the Turing machine Ti. So one can think of, oh yeah, from I can in a computable fashion get a description of the Turing machine Ti, sort of a program for Ti. And can I say yes or no, this does compute the successor? It seems like a boring question. Like, if the algorithms goes and goes, yeah, it adds 1, yes, the answer is yes, it computes the successor. But we will see that we run into a very similar problem as in the halting problem, because in general, it can be extremely messy the way by which it does compute the successor. So much that we will see that the answer is no. This set is undecidable. But just before we address that, let me just rephrase this maybe in more modern terms. Namely, if a fixed algorithm can generically decide if a given program, Python or C or whatever is your favorite programming language, does indeed add 1 or not. It could be a very complicated program to just add 1 to the input. And yeah, we will see that it's undecidable. So in modern terms, can a fixed algorithm generically decide if a given program computes the successor function? And the answer is, I mentioned it, the set IS is uncomputable or undecidable. Yeah, I'm going to stick to undecidable here.
So when you say over there, when you say phi I equals S, you mean identically equal in the function sense. It has the same
yes, exactly.
output behavior.
Yes, good point. This is a function equality. How can we prove that?
Maybe by contradiction, something like that. You assume that it exists, and then somehow you try to build some machine that solves the ultimate problem, and you say like, okay, this is not possible.
Great, great. That's the way to do it. Yeah. We have worked out with a diagonalization process to show that, oh, if the halting problem is decidable, we run into a contradiction. But then to run into a contradiction again, the only thing we need to do is to build a decider for the halting problem. So what we want to do is we're going to assume that there is a decider for IS. And we're going to use it to decide the halting problem. So we would have a contradiction. And we have to reject the assumption that there is a decider for IS. That's the idea.
You can also try to reduce this problem to the ultimate problem. The other option.
That's what it means, no?
Yeah, and then that's what.
Okay, so it's also a proof by contradiction. Proof. Suppose by contradiction that DIS exists. And what we want to show is then that this DIS can be used to decide the halting set. So how do we do that? Yeah, the generic idea is we're going to have like a easy Turing machine that we can code that does indeed compute the successor. We can program one Turing machine, the simplest one that we like. But then we're going to preamble that function with some, don't compute the successor yet, but run Turing machine I on input j first, for a generic I and a generic j. If the computation halts, then compute the successor. So and then we're going to use our oracle dis to ask if our new built function does indeed compute a successor function. If it returns yes, it means that the first subroutine, which has computed ti on input j for generic I and j, will have halted. And if the answer is no, it means that our first subroutine won't halt. That's the generic idea. I'm going to break it down step by step. Please ask and interrogate after we build the more slow process. Now, it's normal that you haven't picked up the generic idea. So first, construct a Turing machine TK it's a little k. So long as I stay consistent, it doesn't matter. That computes S. Note, by the way, that if you're really insecure about the construction of your TK, you can get the encryption of its list, of its rules, E of TK, and then get its index, and use the decider to verify that, yes, it does indeed compute the successor. Okay, so you sort of have this machine which will tell you, you didn't make any mistake in your encoding of TK, it's not an encoding, in your programming of TK. So you compute one that does indeed compute, you produce one Turing machine TK that does indeed compute S. And from TK, we will define a family of Turing machines. From TK, we define a family of Turing machines. T, so I need more labels. I will keep the sublabel K here, and I will have upper indices as well, IJ. For I and J, natural numbers. Okay, so for each ij, I will have a modification of my Turing machine tk. And allowing myself to vary over all pairs ij, it creates a family of Turing machines.
Is that j supposed to be inputs, or?
Sorry?
So, I mean, usually I specifies a Turing machine and j specifies the input to the Turing machine.
Yeah.
Here we have a collection of Turing machines that are like number k. Is the I supposed to mean the k-like Turing machine, and the j is supposed to be an input to that, or?
Let me define tkij, and then it should clarify your question.
Yeah.
This is how they're defined. So tkij, what does it do? On input n, so basically it's going to compute or not the successor function, this function. So on input n, what we want is it returns n plus 1. That's how you have to think about it. But first, it will ignore its input. Doesn't have to do something on input n yet. On input n, do you mind if I take this here? Makes my life easier. One, run ti of j, and if it halts, go to step 2. And step 2 will be something, but before I go on, I'd like to insist on something. I and j are not inputs of the computation. They're hard-coded into that Turing machine. So I'll just write that down, that the parameters I and j are hard-coded in T, I, J, K. And we'll come back to that. But I just want you to note for now that I and j are not inputs. They're embedded in the rules of this machine. The first thing it does, it will simulate Turing machine number I. Oh yeah, I can read I, it's encoded in my rules somewhere. On input j, oh yeah, I can read j, it's encoded in my rules. This is what I mean by hard-coded. And then, if the computation halts, I proceed to step number 2. And step number 2 is run and output Tk of n. Okay, so it really is a modification of Tk. Like, for I equals to 51 and j equals to 17, I have defined some modification of Turing machine Tk, which is first, hold your breath, don't compute, don't execute Tk yet, but run machine number 51 on input 17. And it has already embedded into it the numbers 51 and 17. Then run and output Tk on input n, which should compute, well, this computes the successor. If it happens that Turing machine number 51 on input 17 never halts, this will not reach a halt. So that's it for the prescription of the machine Tkij. Now note that if Ti of j halts, then Tkij does compute S. It's going to go to the second subroutine, and it's going to indeed compute the successor on its input n. And if it doesn't halt, it does not compute S. It's stuck in a loop, and being stuck in a loop is not a function which computes. Well, it's not the Turing machine of a function that computes S. Actually, I should say, is not a Turing machine that computes the function S. Are there questions so far? I'm not done. Are there questions so far?
So TIJK always halts or always loops, right?
Yes. Indeed. Yeah. If the first subroutine halts, it always halts and it computes S in that case. And here it always loops, so it does not compute S. Correct. Now what I want to do is to use that to decide the halting problem. But the only thing I've done is I've defined, one could say abstractly, a family of Turing machines. But I want to embed that into a decider for the halting problem, into an algorithm. So the first thing I should mention, and it's like another note, like note that I'm going to be writing down things, and I'll explain. IJ arrow T I J K arrow E of T I J K arrow index of Tijk. And those arrows means that there's an algorithm for each step. So there's an algorithm which will take ij as input, and, well, this is a bit awkward because this is like writing construct the Turing machine Tijk. Now, if we don't want to think of an algorithm as actually constructing a Turing machine, well, it's going to construct its rules. Okay, so there's an algorithm which will take input ij, and as prior knowledge, if you want, or as prior information, also the function tk. And it's going to construct this Turing machine, Tijk, by this routine, and so on. It has a program. It looks at the program in terms of rules, and those rules have an encoding that we've seen on the first course on computability theory. So this process from here to here is computable. And then, you know, because most of the strings that encode Turing machines, actually, most strings are not valid encodings of Turing machines, but we've seen that we can remove all those that are meaningless and find out the number of the Turing machine, so the index of Tkij. All this is a computable process. So actually my sentence is not done. Note that this is computable. Which, if you like, you could say this way. These intermediate steps are just to help, but we can put all that into a box and call it a Turing machine M. There's a Turing machine M, which, you know, knows about TK and is doing our construction. It takes input ij, and then it's gonna basically construct Tijk and construct the rules of Tijk. That's what matters. And in the end, what really matters is the index of Tijk. Therefore, again, I'm going to use these notations here. On input ij, I could first invoke m to get the index of tijk, and then input that into d of is. The decider, yes or no, are you actually giving me the index of a Turing machine that computes S? And this decider is 1 if that Turing machine, the index of that Turing machine, so the function computed by that Turing machine is indeed the successor. But we've seen that it is the successor if and only if Tij halts. So I can just say if Tij halts. And 0 if Tij loops. So therefore, maybe I should say this would be a decider of K0. So just to repeat the general idea, we start with building one successor function. And we suppose that we have this decider, which tells us yes or no. What you're giving me as an index of a Turing machine does compute the successor function. So as a test, as I said, as a test, I could ask, dis of k, is that equal to 1? Just to make sure, because I programmed Turing machine with some rules. It corresponds to some index k. I'm just going to check. Oh yes, good. I did indeed find a Turing machine tk that computes S. Now from tk, I'm defining a priori, just somewhat abstractly, a family of other Turing machines. I say a priori somewhat abstractly, then I have to make sure that all this is a computable construction. So, and it is, just because I'm basically writing it down as you start from tk and you define first a first subroutine which run tij, and then the second subroutine will run tk. So now notice that, as I said, the parameters ij are hard-coded into tk of ij. But another way of saying this is that, if instead you have knowledge of tk, of its program, of its construction, and I feed you tij, I feed you ij as extra parameters. Can you construct the Turing machine tijk? Well, yes, you construct it just exactly like we've done. So in particular, it has a set of rules, and you look at this set of rules, it would give you, you can encode them into a bit string, and then you can find out the index corresponding to that encoding. So all this to say that this process here is also computable by a Turing machine M. And now to decide the halting problem, we first call M on input ij, which give us the index of tkij. And then we call the decider of is. Because if tij halts, then the decider of is will say, yeah, what you've given me does indeed compute S. So we'll be able to say, okay, on input ij, since the answer is 1, it means that the first subroutine has halted. And if it doesn't halt, well, it will output 0, and it will decide that the first subroutine has not halted. Question?
Index of T, K, I, J. I'm confused as to what that means.
Okay, good. It is not K, it is not I, it is not J. It is the index of that Turing machine. So for fix I and J, you can fix it. This, I'm writing down a Turing machine. I will have to play in the rules of the Turing machine and so on to write that Turing machine down. And then it will have its own encoding of rules, and it will have an index.
What is an index?
Those. 1, 2, 3.
Good enough.
The Gödel number.
Okay, it's position in the ordering of all the Turing machines.
Yes, okay.
This encoding that we...
Yes, yes. Yeah, we gave 2 names to those. When you have T1, T2, T3, T4, the labels 1, 2, 3, 4 of the ordering of all Turing machines was called either an index or a Gödel number. Each Turing machine has, well, it has infinitely many indices. But when it's like explicitly constructed like we have, there's a unique encoding of its rules, and that can correspond to a fixed index, which is computable.
When you say there's infinitely many indices, you mean in the sense up above that there are infinitely many Turing machines that compute exactly the same function.
Correct,
But
yes.
their internal workings are different.
It's a good point. I shouldn't have said that, because each Turing machine has only one index. But each function, partial computable function, since there are infinitely many Turing machines that compute it, has infinitely many indices.
Yeah.
Yeah, good point. Okay. I'm a little bit over time, but it's worth. We're going to be wrapping it up, and so after the break, we start with a new chapter. Definition. An index set that is the name. It's might be a confusing name, but it's the name. An index set I is a set with the following property. Well, I should say it right now. Is a set of Turing machine indices with the following property. If phi I is identically equal to phi j, so I said Turing machine indices. I could have said alternatively partial computable function indices. It is a set of indices. But it's not any set of indices. It's a set of indices that has the following property. If those two partial computable functions phi I and phi j are equal, identically equal, then I is in the set if and only if, I is in the set, capital I, if and only if j is also in the set, capital I. Okay, what that means is that if you find two distinct indices, I and j, well, you find, that implies that you can find them algorithmically. But if you are given two distinct indices, I and j, for the same partial computable function, then either those two indices are in the set, so I is in the set and j is in the set, or they're both not in the set. I is not in the set and j is not in the set.
Is a way to partition your family such that there is no function, like if there are two functions either in or outside of it.
Yeah, exactly. So if you think of our example, we had a function s, then we had a set of indices that were computing the function s. It qualified as being an index set because take the elements of the set. Take two distinct elements of the set is. Well, it might be some I with some phi I actually computing s, and some other label, some other index j with phi j actually computing the function s. And so phi I was identically equal to phi j, and they were indeed both in the set is in that case. Now there were also indices that were not in the set, that's fine. Like all the indices that compute the function square were not in the set is. But that they were consistently all not in the set is, so it was correct. I put words on that. Index sets are a way to describe classes of partial computable functions. Or, another way to think about it, or properties of partial computable functions. Now, if I want to say all partial computable functions that compute either the successor or the divide by 3, well, modulo 3, I should say. Well, I'm defining properties of partial computable functions. And then I want all the indices that correspond to those partial computable functions. And that will define a set of index. It will be all the indices that correspond to either the successor function or the mod 3 function, or whatever is the property that I'm trying to encapsulate. Okay, that was a definition. I have another small definition, and then we can state Rice theorem. An index set I is trivial if I equals to the empty set or I equals to all natural numbers. Okay, if I tell you, hey, I have this defining properties of my partial computable functions, and I will tell you what's the property by telling you what's the index set corresponding to that property, and I say, oh, it's the null set, it's nothing. Where you're not giving me you're giving me a trivial property of partial computable functions, basically. And if you tell me, no, yeah, all indices, it's also a trivial property of partial computable functions. So we call those trivial sets, index sets. We can easily verify that those two sets fulfill the definition of being an index set. And Rice theorem any non-trivial index set is uncomputable. So what we did in the first part is a special case, which was is that when we're applying Rice theorem basically to the set IS, the set of all indices that we're computing the partial computable function being the successor. But Rice theorem is super general. It says that any non-trivial index set is uncomputable. Now let me just raise a flag. If you read this too fast without reading the previous definition, you might say, oh, an index set is just any set of indices, like the set 1, 2, 3. No. The set 1, 2, 3 is not an index set. Because Turing machine, well, partial computable phi 1 would be in your set. And so also all the infinitely many others partial computable function that compute the same thing as phi 1 also need to be in the set. Actually, their index need to be in the set. And same with phi 2 and same with phi 3. So you could say like the set of indices or the index set generated by phi 1, phi 2, phi 3. I guess that could be admitted because you include all the indices that compute the same partial computable function as phi 1, phi 2, phi 3. It will give you, in any case, an infinite set, which is a good sign to have a non-computable set. Because we've seen last time that finite sets are anyway decidable, or computable. I'm not going to do the proof, but it's super analogous to what has been done there. Just change, basically, being the successor with being an element of the set, of the index set. Are there any questions on Rice theorem?
I don't have a clear idea how to prove this theorem.
Mm-hmm.
For each possible, because if you think it's clear, it makes sense. But it's difficult because you have to find a way or to bypass the infinity, the sort of infinity function, or I don't know.
Yeah, reread this somewhat carefully. I'm not saying you cannot copycat this. For example, this line will not work. Construct a Turing machine TK that computes S.
Yeah.
No. But if you have a non-trivial set of index, you can, and you assume by contradiction that you have a decider for it, you can say, let me call D of 1, D of 2, D of 3, D of 4, D of 5, and so on, until you find one member that is in the set and one member that is not in the set. And then the rest should carry through. But yeah, it's normal that it's not clear like that, but it's a bit of work. And it could have been a problem sheet question. It's not. Speaking of which, some people joined a bit late. Who needs a problem sheet? Ali? Okay, so yeah, as I said, the Rice theorem is not mandatory for algorithmic information, but it really is like, oh my god, when you read this, there's a lot of uncomputable sets. It's not just the halting problem. It's any non-trivial property of Turing machines, or any, if we put it into modern computing languages, it's any non-trivial property of a given program. Does this program does that? Yes or no? It's undecidable in general. Because, as I said, you can sneak in the halting problem by the back door. I'm well over time for the break. Please take 15 minutes and let's reconvene at 3:45. All right, welcome back. We finally get to algorithmic information, algorithmic complexity. For the rest of this class, I think I'll just review some but motivate the notion, basically, based on what we've seen so far. Algorithmic complexity. The aim of algorithmic complexity is to provide a quantitative intrinsic and universal measure of information content in a digital object. Okay, that's a lot of promises. It's qualitative, intrinsic, and universal. I say that this is the aim. I shall not today be able to coin the definition and justify all those attributes, but we will eventually in the course of this section. I guess for the rest, I'll mostly motivate what I mean by intrinsic. It really is a property of the digital, I said a digital object. I hope not to confuse people. Digital object can be encoded into binary strings, and so we will be interested with binary strings. Now, you could also speak of the algorithmic complexity on a different alphabet, if you will, but we will restrict ourselves to binary strings. Yeah, okay, as a motivation, we'll check two examples. Yeah, so if that is a large section, then this is a subsection, if you will. Okay, my first example is communication. We'll come back to communication in a somewhat in a different context. we have seen that Shannon theory of information was a way to measure how many bits we need to communicate if we have symbols that are coming by a random process. Now, example, communication. There are contexts in which it is unsuitable to look for an underlying probability distribution. When we aim at communicating a string of symbols. All right, this is the program of Shannon information. We have an alphabet made of symbols, and we conjecture that this the symbols are generated by a random process with some distribution on that alphabet. Now just to remind you where we were, the whole idea was to reserve shorter code words for likely events and larger code words for unlikely events. And the idea of a prefix code, it was a code that we could concatenate the stream of symbols or the string of symbols so that the receiver knows how to uniquely decode them by reading them from left to right. Now what I just wrote here is that in some cases it's not really appropriate to say that, oh yeah, this source of symbols comes from a probabilistic process. And the example that I'm going to build now is this one. For example, what should we do if Alice wants to communicate this? It has 10 to the 10 digits. And we recognize them as being the first digits of pi.
Is 9 actually the 10 to the 10th digit of pi? Or did you make that up?
Should I bluff or? Yes!
Because I think it is computable, right? You don't have to compute them in order. Like, I think there is a function that just computes a given digit.
That's a recent discovery, isn't it?
It could be, yeah, I don't remember.
I saw that on Twitter, but some physicist I follow sort of said, yeah, there's a recent paper, you can just... I think, if my memory is correct.
Yeah, it could be.
But it might be a recent result. So Alice wants to communicate this. Let me say space and just write to Bob here. So Alice is the sender of a message, Bob is the receiver. Now, the truth is, when we apply Shannon information in concrete settings, we're not given the distribution. In some cases, we might. There might be some processes that we are given a distribution and we blindlessly apply Shannon's tools to find an encoding of the symbols. But in most cases, we're not given a distribution. We have to figure it out. So in Shannon theory, one might say, oh, that's a bunch of symbols, okay. And I'm going to compute frequencies. And I'm going to realize that the amount of the frequency of the digit 3 occurring is roughly 1/10. And the frequency of 1s is roughly 1/10. And the frequency of 4 is roughly 1/10. And so by doing that, one might assume that, oh yeah, it's sort of a random process with a uniform distribution over the alphabet 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and the distribution is uniform, so I'm going to encode them into 4 bits per symbol, because 4 bits would provide me with 16 possibilities. And so applying Shannon this way, one might elect to communicate 4 times 10 to the 10 bits of communication. And maybe somebody a bit clever might say, I'm going to use some technique that we haven't seen in this course, but we don't really need to. Blocks encoding instead, to reduce this constant 4 to something that looks a bit more like log of 10, 3 point something. But because we don't exactly need 16 possibilities, we only need 10 possibilities, and there's some tricks you can use. But you're not changing the bulk of the thing. You're still sending many, many, many bits. Why? Because, as I say, there's no really an underlying distribution for this sequence of symbols, but you sort of assume there is, and you're trying to find it. And you conjecture like basic ones, like, oh yeah, each symbol is independent and uniformly distributed, so I'm going to apply Shannon's theory with that idea in mind. But the generic idea behind AIT, Algorithmic Information Theory, is to assume that the string has been generated by an underlying computation. And not an underlying probabilistic process.
But can't you think of both of them like a randomized algorithm?
Yep. It's gonna to see computation, it will occur. We will find this idea that it's sort of, you have a computation which has sort of a seed, and this seed is like a fixed bit string. Then you're free to understand it as randomness or just as extra information in the computation that is large. Yeah, but yeah, keep your idea in mind. It will come back. So in the context of communication, the sender, which is Alice, and the receiver, Bob, are equipped with universal computers. Right, and Alice is not going to be looking for probabilistic processes that might have generated that string, but for computations that might have generated that string. And Alice may communicate something like the first 10 to the 10 digits of 4 times the sum n to 0 to infinity minus 1 to the n over 2n plus 1. That is a sum for pi. It's a much shorter message, even if we put that into binary. It's a much shorter message than something like 4 times 10 to the 10 bits to communicate. So Alice communicates this. She communicates the description to run on a universal computer, and Bob will decode it by expanding this description. So my sentence is not finished. It is not finished. Alice may communicate this, comma, which Bob runs on his computer to decode.
It's kind of like sending I and J for a Turing machine. Like the sum is I, and the first 10 to the 10 digits is J. Like the Turing machine that computes digits of pi.
Yeah, okay, so you're sort of
10 to the 10.
breaking already this description into two pieces which contain information. Sort of this would be one, and this would be one. Yeah.
Yeah, like which Turing machine to run and on which output.
Yeah.
Or which input, rather.
This idea will also be useful. Keep it in mind. Pasquale?
So pretty much, Alice, instead of sending the message, she's sending the program to compute the message.
There you go.
But what if you have some message that you cannot compute?
Yeah.
What do you do?
Is the message finite?
No, that's
Yeah, because if it's finite, it's always computable, but you may be putting your finger on the fact that the program for that will be very large, perhaps as large as the string. Yeah. Well, then it will have a large algorithmic complexity.
it's not finite.
If it's infinite, then you have an uncomputable.
So you cannot send it.
You cannot send it. Yeah. But anyway, to send a message already assumes that you're sending a finite amount of information. I could still, one could make a case that I'm going to send a non-halting program that's going to print all the bits of pi, but I'm going to send it in a finite program, and then we might get there too in the theory, but it's not critical aspect to try and formally define how to send an infinite string. But the theory has place for that. It can accommodate a finite description of an infinite string. Well, basically just like that. What I'm doing here is I put a cutoff to make sure that even once extended, it remains finite. I have another example. Yeah, okay, so that example was to maybe just revisit communication in the light of, sometimes there's some cases in which algorithms might be more interesting to encompass a short description of what I want to send. And this here is my short description of what I want to send. It's better to do that than to view pi as a probabilistic process. Other example is randomness of individual object. That's just the name of my example. Okay, is this string random? 0, 1, 0, 1, 0, 1, 0, 1. Suppose it has 10 to the 6 bits. So you know how much I'm hiding here. I ask you another question. Is this one random? It also has 10 to the 6 bits.
Well, just the fact that for the first one, I didn't have to look at the whiteboard to write it down, and now I have to copy it one by one.
You're nailing the notion.
Normal definition.
Actually, there's wisdom in what you're saying there, Lorenzo. It grasps the idea. I sort of know that you already have a bit of an idea of what Kolmogorov complexity is. We're motivating the notion. I will call it, by the way, algorithmic complexity. So we would like a notion. So I'm just gonna put it as some desiderata, and we'll it's gonna become clear once we have the formal notions. We would like to say that the first one is not random. And that the second one is a bit more tricky. I'll say at least appears to be random. Again, I have not said what random means, but I'm really defining some sort of intuitive notion. I'm not defining it. I'm appealing to an intuitive notion. But how can this intuitive notion of random be formalized probabilistically?
Can you apply, I don't know, Shannon entropy to that?
Yeah. You can apply Shannon entropy to blocks of 2, and you will have you'll realize that it's always the same symbol. But let me just say, you might also be tricked. Like, it might actually be the case that both of those strings came from a Bernoulli process. You have 1 chance out of 2 to the power of 10 to the 6 to get that string by chance. You have the same probability, by the way, to get that string by chance. So if really like they both come from a Bernoulli process, you might say, yeah, that's random. And that's as random as that. But then it seems like we're missing an idea that this one is full of patterns. And so it disqualifies as being random. Whereas this string appears to be patternless. And so it would qualify to be called random. So just the probability, again, as I say, first you need to conjecture that it comes from some process, like a Bernoulli process. I made it up. If it comes from a Bernoulli process, then this string is as likely as that string, probabilistically. I think I'll erase this.
No, it's not.
Oh, thanks.
But we have a formal definition of random.
Yeah, we will. In probability, I don't know.
The thing is that I know that in cryptography you cannot have anything really random. Like your maximum pseudo random. Like random doesn't exist.
Yeah. We did the axioms of probability theory in this course. At no point was an axiom of randomness, what it was called to be randomness. You know, we had a probability measure on a space, we had a space of events. Nowhere we can say like, yes, this is not random, this is random. In algorithmic information, we will have a notion. By the way, I'm elaborating on that. If viewed as arising from a computation instead of a probabilistic process, the patterns displayed by the first string amount to a short description of it. For example, print 0, 1, 10 to the 6th times. Oh, maybe divided by 2.
Yeah.
On the other hand, if really the second string has no patterns, then there's no short description of it. The shortest computable description for it might be print quote, and I have to quote this string 0, 1, 1, 1 0, 0, 1 triple 0 1, 0. Okay, I'm tired. Finishes by a 1. Okay, so I'm giving the intuitive idea of what's the intrinsic randomness in a string by demanding, is there a short computable description for the string? In the case of the fourth string, we exhibited one. Print 0, 1 for 10 to the 6 over 2 times. It's a short program that we can run on a universal computer to get to that string. On the other case, I cannot tell you for sure, but suppose that this string is indeed random in the sense that there's no pattern, or in the sense that if I'm looking for short descriptions of it, the best I can find is actually to quote the string itself. Print, and I have to quote the string. If that is really the shortest computable description that we can give on a universal Turing machine, then we will say that that string is indeed algorithmically random. So we have a notion of intrinsic randomness. It's not a matter of by which process that string has happened to occur. It occurred by a Bernoulli process, but we were lucky. We got 0, 1, 0, 1, 0, 1, 0, 1. We could always invoke luck, by the way, because each million-bit long string that will be generated by a Bernoulli process will all have the same probability of occurring. So we can always say, I have been lucky. I've got that. Whereas here we have a notion that is rooted more into computability and forgets about probabilistic processes. How am I doing with time? I might be over time. Yeah, I'll just say it, but both examples motivate us to look at minimal descriptions on a universal computer to assess the quantity of either randomness, or I also mentioned here information content. I mean, a notion of randomness amounts to a notion of information content. You can think of it in terms of entropy. There was a lot of information, or there was a lot of randomness in a distribution. And if there was a little bit of information, a little bit of information, then it has short entropy. We have the same duality here. So a good measure of randomness is also a good measure of information content. Questions? Cool. On Thursday, we will look into the formal definitions. Have a nice week.